putin banduit. Rick, good morning.
Good morning. As data rates go to 50 gigabits per second and greater, what's going to happen is it's going to be critically important to understand the differences between OM3, OM4, OM5, and signature single mode fiber. And this is going to be a technical presentation, and I'm going to describe the differences between these different fiber types, when to use one versus another one, when to use single mode fiber. I get a lot of questions. Should I deploy single mode fiber so that I can future-proof my network, or OM5? So these are the kind of questions we're going to address. Also, what you'll find out is that for 50 gig and beyond, you can no longer use copper cabling for many of the applications. So we'll go through all of that. So we'll begin by pointing out that multi-mode fiber will continue to provide three primary benefits over single mode fiber. And the most important, of course, is cost. VCSELs, vertical cavity surface emitting lasers, which are multi-mode lasers, are surface emitters, meaning that you can make these devices in wafer form. They're typically manufactured on a 100 millimeter wafer. About 100,000 devices are processed on one piece of material, wafer. And they can be completely processed, tested. Bad devices are marked with ink. You can burn them in, put them. You can do almost all the processing and testing of these devices in wafer form. At the end, you dice them. For multiple lasers, you dice them in arrays. You mount them into your transceiver, and it's a low-cost operation. Single mode transceivers are inherently more expensive. I have an image of here. This is a VCSEL. This is a distributed feedback single mode laser. The difference between single mode lasers and VCSELs are DFB lasers are edge emitters. All single mode lasers are edge emitters, which means that the light actually comes out of the edge of the device as opposed to coming out of the surface device through this lens area here. Because it comes out from the edge, after you manufacture the laser, you have to then dice it, mount it onto a header, onto some material. The materials are pretty exotic materials because they have to be able to dissipate a lot of heat. Single mode lasers actually dissipate 10 times the amount of energy, heat, as multi-mode, so they're a lot hotter. You have to dissipate the heat, you have to wire bond them, and then you burn them in and test them. And you get a large fallout. And because you get a large fallout, the cost of these devices become very, very expensive. And that's going to continue to happen. So single mode fiber will continue to be more expensive than multi-mode. The other reason why multi-mode has benefits is in terms of just the size. Because not only the size, but single mode fiber, single mode connectors, when you get scratches on them, those cause reflections on single mode. As you start cleaning connectors and you add scratches, you get reflections. That's measured in return loss. You want a high loss. You don't get many reflections. But those reflections, single mode is a coherent light, which means it interferes with itself. So when it goes through, hits a connector boundary and reflects back, it actually can get back into the laser cavity, and it does get back into the laser cavity, and it's phase shifted, so the electric fields actually interact and combine, and they destructively interference, and you could actually have very high losses. And the losses can depend, even putting in a connector, a patch cord, you can get multiple reflections in the patch cord. That's called multipath interference, and you get high losses. So there's a lot of problems with single mode. It's really designed for the long haul, long distance communications. The other reason that multi-mode is going to be around for a long time is that it will need all the data rates for the next 20 years or more in the reaches, and that's what we're going to really kind of talk about. So I'm going to focus mostly on the differences of multi-mode fibers and when to use them in the network. Here's when we get a little technical. In order to understand what Ohm 3 is versus Ohm 4, Ohm 5, and what the differences are, that's where we have to get a little technical. So I'm going to get a little deep into that. But what's very interesting also is the power penalties that are important as we move forward into higher data rates. There's also, in order to get these higher data rates, you'll see that people are using what we call parallel optics. Those are multiple fibers. Those of you that may have deployed 40 gigabit Ethernet, you know they're on MPO connectors. You have 4 parallel pairs, each carrying 10 gig per pair. Parallel optics is what is the future, and I'm going to show you why. We'll talk a little bit about single mode applications, and then looking forward about 15, 20 years out, what is actually going to be in the field. So I think everyone here is, when you build a link, everyone's usually interested in insertion loss. At 10 gigabit Ethernet, 10 gigabits insertion loss is the only power penalty that you have to be concerned with. It's also the only one that you're in control of. But it turns out there are 7 other power penalties that affect the link and limit the link that you're not aware of, or maybe most of you are not aware of. Things like ISI, which is intersymbol interference. That's actually the largest power penalty in a channel. Modal noise, mode partition noise, relative intensity noise. These are all power penalties that cause noise in the channel and have to be accommodated for. So in the IEEE, when we write a standard, we argue over these numbers, what should they be? So we put in budgets into the standard so that you don't have to worry about them because you have no control over them. The only thing you have control over is insertion loss. And up until now, insertion loss was critically important. I want to point out that insertion loss is also independent of data rate. It's just optical attenuation. Now look at this chart. You look at 1 gig, 10, 40, 100, 128, and what you see is the reach went from 550 meters down to 85 meters for 125 gig. And if you look at the optical attenuation of just the fiber attenuation is going from 2 dB all the way down to 0.3 of a dB. The loss has gone down to practically nothing. And yet the reach went from 550 meters down to 85 meters. It turns out that what's important now is the intersymbol interference. And again, you don't have control over it directly, but the way you do have some control over it is selecting the type of multimode fiber that you use. I'm going to describe what intersymbol interference is, and that's where we get technical. So intersymbol interference is the primary penalty that's going to limit a channel from 50 gigs and beyond. Insertion loss is, I hate to say it, but it's actually not important. As an example, it's important for other reasons. Insertion loss, it's not the attenuation that's going to kill you. It's what happens when you have connectors that are not very well aligned. What happens is it creates another power penalty called modal noise, which is that, so you do increase modal noise if you don't have, high quality, low loss connectors. It's just a different power penalty. So let's talk about intersymbol interference. When we talk about multimode fiber, what a mode is an optical path. It's nothing more than an optical path. when you have a wave, light is a wave, waves interfere with themselves. And they can only propagate in certain ways. An example would be a guitar string. If you have a guitar string that's constrained on both ends of the guitar, and you pluck the string, that string can only vibrate with a fundamental frequency and all its harmonics. If you tighten up the string, you get a different set of frequencies. Those are modes. And you have modes because the wave is constrained somehow. It's the exact same thing in fiber. The fiber is a waveguide, and you have light that's propagating, which is a wave. So the light can only propagate in certain ways, so it interferes with itself constructively. And it turns out that in multi-mode fiber, there are only 380 different modes or paths that the light can take so that it constructively interferes with itself as it propagates through the fiber. And what I show here are 3 examples of 3 modes. You have what's called low order modes, which propagate close to the fiber core. You could have ones that look like sinusoidal, kind of like a guitar string. You even have modes or paths that take corkscrew paths. So what you can see is if light goes straight down the fiber, it's going to get to the end of the fiber quicker than, say, light that's going down, in some other more complex path. What's also important to realize is when the light gets emitted from a VCSEL, a laser, it illuminates the core of the fiber, and that light splits and takes all the possible different modes that it can take. So the light isn't carried by one mode, as it is in single mode, but it's carried by hundreds of modes. Okay? So what you have to do in multi-mode fiber is you grade the refractive index. The refractive index is the optical density of the fiber, and it determines how fast the light propagates. So what you do is you grade it such that in the center of the fiber, in the center of the fiber, you have a high refractive index, high optical density, so the light that's propagating down the center of fiber is actually slowed up. It slows down, whereas light that's propagating towards the cladding sees a lower refractive index and actually travels faster. And the key is, what you try to do is grade the refractive index of the core such that all the modes are equalized. No matter what optical path the light takes, it's going to get to the end of the fiber at the same time. Okay. It's a problem, though. The problem is no one can make a perfect fiber. None of them. No fiber is perfect. And because of that, no fiber looks like this. And there's a number that I want to point out because it's very important to understand the differences between the different multimode fiber types. And that's the alpha. The refractive index depends on this alpha number. And what I'm showing, this curve represents alpha, say we'll call it alpha 0. So this is what you shoot for when you make a fiber. But what you get is something that looks like this. It's either, it's a little less of a shape or a little bit more. And if it's less than alpha 0, we're going to call that alpha 1. And if it's more than alpha 0, we're going to call that alpha 2. And these fibers that are made, so what we're saying here is that every fiber will have either alpha 1 or alpha 2. It's not going to have alpha 0 because you can't really get that. The alpha 1 and the alpha 2 actually perform very differently. So if you buy an ohm 3 fiber, ohm 4, half of your fibers will work one way and the other half will work a different way. And that's, I'll show you why that is. So the first, ISI has 5 contributions in a channel, this intersymbol interference. One of them has to do with the transceiver, so we're not going to talk about that. One of them, which we will talk about, comes from a combination of the fiber and the VCSEL. This is something the industry didn't know till about 9 years ago or so, 8, 9 years ago. But there's a contribution of the combination. And then there are 3 contributions that are just due to the fiber, okay? So let's say we have 2 bits, we're sending 2 bits down an optical fiber, and what's going to happen is the light's going to expand and it's going to get coupled into all the possible modes or paths it can take. And what's going to happen is if the alpha, in this case, is greater than alpha 0, that means you kind of overshot what your refractive index profile is supposed to look like. The modes that are propagating at the outer regions are going to see a lower refractive index, a higher refractive index, and they're going to get to the end of the fiber later than ones that are propagating towards the center of the fiber. This is called modal dispersion. This is what, so when you buy an OM3 fiber, OM4, OM5, what they do is they measure this modal dispersion, and from this they calculate the bandwidth and effective modal bandwidth. It's the modal dispersion that they actually measure. So because you have dispersion, what that means is that when the light hits the detector in your receiver, all the different modes are going to get there at different times, so now the pulse is broadened and you have modal dispersion. And the way that hurts you in terms of intersymbol interference is if you put two bits together, as you start going higher and higher data rates, as you do with 25 gigabit and beyond. So 10 gigabit, this hasn't been too much of a problem. Insertion loss is what limited the channels. But when you start packing these data bits close together, as you're doing 25 gig and 50 gig and beyond, they're so close that this dispersion, this modal dispersion is going to destroy your performance. So if you go through the fiber, you'll see this thing spreads out. And if it spreads out too much, you get what's called intersymbol interference. So in this case, what we're saying, the bits are actually called symbols. And that's where you get the term intersymbol interference. Bits is just a way, that's just a measurement of the data rate, but these are actually referred to as symbols that are propagating. Now, here's the second contribution to ISI, which is also becoming very important because of multiple wavelengths. When you overshoot or undershoot the refractive index profile of the multimode fiber, what you're actually doing is optimizing the fiber for a different wavelength. That alpha that they shoot for, which is a value of 2, is to optimize and equalize all the modes at 850 nanometers. So if you overshoot or undershoot it, what you're doing is you're optimizing it for different wavelengths. Now, what I show here are two different multi-mode fibers from the same manufacturer in the same cable with the same bandwidth at 850 nanometers. And what you see is one is optimized because it has an alpha less than alpha 0, the other one has one greater. You can see they're optimized at totally different wavelengths. So if you try to use half of your fibers that have alphas that are alpha 2, which is greater than alpha 0, it won't work at longer wavelengths because the bandwidth just drops very high. So this is not this will not support multiple wavelengths, whereas the other fiber, in fact, will. The other thing is how it affects intersymbol interference is that transceivers are specified to have a wavelength of 850 nanometers. Unfortunately, very few of them have 850 nanometers. They can vary plus or minus 10 nanometers. So the bandwidth is measured at 850, but you now put it into the field with a VCSEL that is, say, 845 nanometers, and depending on which fiber you have, you could have a very big difference in actual bandwidth, modal bandwidth, a modal dispersion. So it impacts your intersymbol interference again. This is some data we calculated for Cisco. We worked with Cisco, and this was actually for the BiDi. We worked with Cisco in the introduction of the BiDi, which is 40 gigabit, 2 wavelengths, each working at 20 gig. And they wanted to know how far will these transmission signals go. And what you can see is that the fiber that has alpha 2, which has very low bandwidth at the longer wavelength, will not support a 100-meter reach, which was the requirement for Cisco's BiDi, whereas the alpha 1 fibers do. This is because it is, in fact, let me hold off before I tell you a little bit more about this. There's now another